In the previous video, we looked at using the Kruskal-Wallis test in order to conduct an omnibus test of the hypothesis of the equality of medians in K conditions. In case you don't know the term omnibus hypothesis test, that simply refers to conducting a single test of a hypothesis about more than two groups. But that leads to a question. When you find that there is a difference among more than two groups, where are those differences? Is it group 1 is different than 2, 1 different than 3? Conducting an omnibus hypothesis test and rejecting a null hypothesis simply tells you that there are differences somewhere. It doesn't point to where those are. In order to address that, we need to do multiple comparisons. So this presentation is the follow-up to the Kruskal-Wallis presentation, in which we look at multiple comparisons with ranks. One of the most commonly used designs in behavioral and social research involves the comparison of scores in K conditions where K is greater than 2. The Kruskal-Wallis test is based on ranking observations. As such, it can provide more power than the parametric one-factor ANOVA when population distributions have higher kurtosis than the normal distribution. Yet we may wish to either forego the Kruskal-Wallis test in favor of rank-based comparisons of pairs of conditions, or follow up the Kruskal-Wallis results with rank-based comparisons of pairs of conditions. The only package in R that is required to follow along with this presentation is the coin package. Here's the setup. We have random samples from K populations. K can be greater than or equal to 2. That might mean that we have K independent existing populations to be compared and we sample from each of those, or it may mean that we sample from one population and then represent potential populations by randomizing the participants in our one sample into multiple samples. We have independent observations within each sample and a quantitative response measure. Here's an example. A study of the effectiveness of metaphors compared 3 conditions: a control condition, an advanced metaphor condition, and an extended metaphor condition. Participants in the control condition received a difficult textual passage. For the advanced metaphor condition, the same passage was preceded by a familiar metaphor. In the extended metaphor condition, the metaphors were embedded in the passage. All participants completed a comprehension test about the passage. If we want to do planned pairwise comparisons, pairwise meaning checking individual pairs one at a time, we would have these hypotheses. Is the median of the first group equal to the median of the second group? Remember, by group here, I'm talking about the population, not the sample. We don't need to conduct hypotheses tests about the samples because we can obtain those sample medians. So this is about the population parameters, the median of group 1 and 2, and the alternative would be that they are not equal. Similarly, we can compare the median of 1 to the median of 3, and the alternative is they're not equal, and so on for as many pairs as you have. In this case, we have 3 groups, so we have 3 pairs. We assume the pairs of populations have the same shape. However, research has demonstrated that slight differences in shape can still result in reasonable approximations. That's because location has more weight on our test statistic than shape does. For each pair, we use adjusted alpha with a Bonferroni adjustment. The Bonferroni adjustment is a simple adjustment where we take our nominal alpha and divide by the number of comparisons that we have. So when we have 3 comparisons, we would take the nominal alpha, say 0.05, and divide by 3, and that provides us alpha prime, that is, the alpha that we should use for each comparison. What does that give us? That gives us a family-wise type 1 error rate of our nominal alpha. So if alpha is 0.05, the family-wise type 1 error rate would be 0.05. That means that we will be 95% confident that all of our confidence intervals will contain the true parameter. We can employ the Wilcoxon rank sum test for each comparison. We learned in an earlier video about the Wilcoxon rank sum test as a test for two independent samples. Note here that we have 3 pairs, meaning that we have 3 situations in which we have 2 independent samples. So we'll employ the Wilcoxon rank sum test 3 times. Here I'm setting up for the pairwise confidence intervals. First, I'm entering in the data for each of my conditions, the control, advance, and extended. And then I'm creating factors for each of the conditions, and I'm doing that separately. The reason I'm doing it separately is that it's going to make it easier for me to combine 2 conditions at a time, as you'll see in a moment. Here's the Bonferroni adjustment. I'm going to use 0.10. Why 0.10 instead of 0.05? Well, notice I only have 4 in each condition for a total of 12 participants. This is a very small study, and if you want to obtain more information, you have to pay the cost, and that cost is getting more participants in your study. With this many participants, I don't believe I can be 95% confident and obtain much information, so I'm going to use a family-wise type 1 error rate of 0.10, so I'll be 90% confident in the complete set of intervals. My alpha prime, therefore, is 0.10 divided by 3, and my confidence level is going to be 1 minus alpha prime, but that's only for each individual comparison. My overall family-wise confidence level, which is what I'm going to report, is going to be 90% for the entire set of intervals. Here's the advanced control comparison. Now you can see why I set up these scores and conditions for the separate groups, because I can easily combine the 2 groups that I need. Once I have these 2 groups combined, I'm doing a Wilcox test. I'm using the coin package here, which will allow me to get an exact distribution even if I have ties. I'm setting up for a confidence interval, so I set that to be true to turn it on. And then I provide for the confidence level, that confidence level for the individual comparison. And you can see that's what appears down here for my confidence level. This is going to give me 90% confidence for the entire set of 3 comparisons. So I end up with a confidence interval here that tells me when I compare the advanced metaphor condition to the control condition, focusing on the median difference. Remember, the median difference is estimated by our Hodges-Lehmann estimate. If you do not know about that, go back and watch previous videos where I mention the Hodges-Lehmann estimate. This ranges from -6 to 7, meaning that the advanced group may be doing better, or the control group may do better in the population, or there may be no difference. This is not a very informative interval. Really, the only thing it tells me is that if there is a difference, it's no more than 7 points. That is, the median of differences would be no more than 7 points. Here I'm going to do the extended and control comparison. Extended metaphor compared to control. Again, I'm able to set these up quite easily because of how I set up the data to begin with. And here I am conducting the Wilcox test. That now gives me an interval from 1 to 11. That's a bit more informative. That tells me that extended metaphors do in fact help. Now, they may only help a little bit, only by a median difference of 1 point, or they may help a lot, a median difference of 11 points. But nonetheless, I know that they help. When I compare the extended to the advanced comparison in the same way, I don't know if they help, but if the advanced condition does better than the extended condition, it's only by a tiny bit, 1 point. Whereas if the extended condition does better than the advanced condition, it might be a lot, as much as 12 points. And again, we're looking at the median difference. Throughout all of this, in all three of these comparisons, don't forget to focus also on what actually happened in your sample. In this particular case where I compared advanced to control, I had a median difference estimate of minus 1.5. That is, theta hat sub d is minus 1.5. That minus 1.5, because of the way I'm doing the subtraction here, indicates that the advanced metaphor condition did better than the control condition in the sample by a median difference of 1.5. So don't jump right to inference without paying attention to what happens in the sample, because that is our single best guess of the population parameter. Here we find that we had a difference of 5.5 extended over control. So again, that's our best estimate. Now, that as a point estimate, we can't put any confidence in, which is why we constructed the confidence interval. But nonetheless, the best single guess at what the parameter is 5.5. And similarly here, when we compare extended to advanced, we had a difference of 7 points. Not enough to be able to have 95% confidence, but it does give us hope that extended metaphors, especially when I compare across all the results, that extended metaphors may be the way to go. What about if we want to do the omnibus test first? What I was just doing were what we call planned comparisons. That is, we're skipping the omnibus test and going right to planned comparisons. We would use the exact same process for post hoc intervals, but if you want to maintain your type 1 error rate, and you should, you only go to those intervals if you reject the omnibus null hypothesis. If you do not reject the omnibus null hypothesis, you are done. At that point, you say you do not know if there are any differences. So your choices are to skip the omnibus hypothesis and go right to planned comparisons, or to conduct the omnibus hypothesis and only go to comparisons. That would be post hoc comparisons if in fact you reject the omnibus null hypothesis. In the previous video, in which we used the Kruskal-Wallis test, we did indeed reject the omnibus hypothesis with these same data, so we would have gone to the post hoc confidence intervals that I just showed you.